LSM trees are impressive. Excellent write throughput, sorted storage, elegant compaction. And yet when you look at the storage engines powering almost every relational database in the world, PostgreSQL, MySQL, Oracle, SQL Server, you don't find LSM trees. You find B trees. B trees are older than LSM trees. They've been in continuous production use for 50 years. And despite everything the database world has invented since, they remain the dominant indexing structure. Like SSDables, B trees keep key-value pairs sorted by key, so range queries and sorted lookups are efficient. But the fundamental design philosophy is completely different. Log-structured storage breaks the database into variable-size segment files, several megabytes each. B trees break the database into fixed-size blocks called pages, traditionally 4 kilobytes in size, matching the block size of physical disks. The database reads or writes exactly one page at a time. Each page contains an array of keys and references to child pages. One page is the root, where every lookup starts. Each child page is responsible for a continuous range of keys. You follow references from parent to child, narrowing the range at each level, until you reach a leaf page that contains the actual value. The number of child page references in a single page is called the branching factor. In practice, branching factors of several hundred are typical. And the numbers this produces are remarkable. A B tree just 4 levels deep, with 4 kilobyte pages and a branching factor of 500, can address 256 terabytes of data. Most databases never come close to needing more than 3 or 4 levels. This structure is what makes B trees fast for reads. You follow a path from the root to a leaf, and the path is only a few levels deep no matter how much data you have. But keeping that path intact through writes is where things get complicated. Here's the critical difference between B trees and LSM trees. B trees overwrite pages on disk in place. When you write to an LSM tree, you append to a file, you never modify what's already there. When you write to a B tree, you find the page where the key lies and overwrite that page on disk. On a spinning disk, overwriting means moving the disk head to the right location and overwriting the magnetic sector. On an SSD, it requires erasing and rewriting an entire block, which is why SSD writes are more expensive than SSD reads. Most of the time, updating one page is enough. But some operations require overwriting multiple pages in a single logical operation. The clearest example is when a page fills up and needs to split. A page split means writing 2 new pages plus updating the parent page to reflect the new child references. 3 writes, all part of the same operation. Now imagine a crash happens halfway through those 3 writes. The parent page has been updated to point to a child page that doesn't exist yet. The index is now inconsistent. Any lookup that traverses that path will get a wrong result, or worse, a crash. To prevent this, every B tree implementation includes a write-ahead log, also called a redo log. The write-ahead log is a separate append-only file on disk. Every modification to the B tree is first written to the log before it's applied to the tree pages. If the database crashes and restarts, it replays the log to restore the tree to a consistent state. Concurrent access adds another layer of complexity. If 2 writes happen at the same time to the same part of the tree, they need coordination. B trees use latches, lightweight locks, to protect the tree's data structures from concurrent modification. All of this machinery adds overhead to every write. Which leads to the most practical question of this chapter: when should you choose B trees over LSM trees, and when should you choose LSM trees over B trees? The book is direct about this comparison. As a rule of thumb, LSM trees are typically faster for writes, and B trees are typically faster for reads. Here's why reads are slower on LSM trees. To look up a key, you check the mountable, then the most recent SSDable segment, then the next older, potentially checking many levels before finding the key. B trees always follow a single deterministic path from root to leaf, no searching across multiple structures. Now, both B trees and LSM trees have something called write amplification, data being written to disk more than once for a single logical write. For B trees, data is written at least twice, once to the write-ahead log and once to the actual tree page, and sometimes more when page splits cascade up the tree. For LSM trees, compaction causes the same data to be written and rewritten multiple times as it moves through levels. But there's a key difference in how those writes happen. B tree writes land wherever that page happens to be on disk, a random write. LSM tree writes are always sequential, flushes to disk go to the end of the current segment file, and compaction produces entirely new sequential files. On both spinning disks and SSDs, sequential writes are dramatically faster than random writes. LSM trees also compress better. Because compaction actively removes redundant data and old versions, the resulting files are smaller. B trees leave deleted data in place and can accumulate fragmentation over time. But B trees have one advantage the book highlights as particularly important for databases: each key exists in exactly one place in the index. In an LSM tree, the same key can appear in multiple SSTable segments at different stages of compaction. In a B-tree, there's exactly one copy. That single copy property makes it straightforward to implement transaction isolation using range locks. You lock a range of the B-tree to guarantee nothing else can modify those keys while your transaction runs. The conclusion: neither is universally better. The right choice depends on your workload. Write-heavy systems lean toward LSM-Trees, read-heavy or transaction-heavy systems lean toward B-trees. And for many real systems, the difference is smaller than the benchmarks suggest.